estimate the correlation properties of a random process. Okay? So, in order to make these spectral analysis is typical. You remember when I put a spectrogram where there was music and it was talking, you see the frequency content, right? Okay. That one I was doing a time varying spectral analysis. So which means I'm evaluating what is the frequency content in signals. Okay. I was discussing with one of my former student, okay, that made a thesis with me. Now he's doing the PhD with a physicist. And he says every day the physicists, they make a spectral analysis. They don't know what they're doing. And most of the case, they are following all the mistakes. You are talking to us, which means, I was talking to him. And so he says that, he's spending a lot of time about explaining the physicists how to read resonances in signals or similar, okay? Because they fail, they make many mistakes, so, anyway. So this is just, what it's about. Now, usually, the spectral analysis, I'm anticipating, so it's a basic, okay? So we will discuss much in detail later. So, but the spectral analysis is based on the so-called the autocorrelation sequence, okay, which is defined in this way. Now, the spectrum is the Fourier transform of the autocorrelation sequence. Okay? That's it. And spectral analysis is to estimate the spectral content in signals by using X, where X is a limited set of signals. So if I have virtually an infinite number of samples, everybody can do spectral analysis. But if I have a limited set of samples, that's more difficult. So as I told you, we're not dealing with a huge amount of data. We are dealing with a limited set of data because the data are expensive. Now, don't write anything on that. It's just to motivate why we are discussing this topic. Now, there are different ways to estimate the power spectral density, okay, which is the Fourier transform of the autocorrelation, which I have not defined yet. Okay? So, but there are different ways, and different way is related to the way I can describe the mechanism that the random signal is generated. Now, that means that we need to study a little bit more about these random signals, because this is the basis of everything that we are going to do about spectral analysis, measuring for instance, one of the issues that he has to work with, he was telling me a couple of days ago, is that these physicists, they need to work a lot on hidden periodicities in signals. Okay, hidden periodicity in signals. So, that's another aspect, okay? So you need to know what you're talking about. So this is the topic of today. Now, what is a random process? So, let's start today. What is a random process? A random process is simply a set of samples that are random, ordered in time. Sometimes they're called a random time series, okay? Because I have a series of samples that they are random, so they have random properties. Now, so what is beyond the definition? Let me have a page because Now, for many of you, all I'm saying is just a refresh of a well-known topic, and for few of you, that would be just the first time you see or similar. Okay. So up to now, if we go back up to now, what we have seen? We have seen that I can define the probability density function of a random variable. I can define a joint probability density function of two or more random variables. I can take these random variables and stack, which means order, into a vector. And so, let's look at these aspects. So for instance, what we saw is the following, that if I have a vector x which is containing a set of random variables, which is xn. Okay, this is what we know. So we can define on this random vector the moments. And so the typical moment we define is the first moment and the second central moment. We have already seen. So the first moment is the mean. So we can define the mean of that, which is is taking the expectation of the vector x, okay, which is composed by the mean for all the entries. Fine. We can define the second central moment, which is the correlation and the covariance matrix. And the covariance, by definition, which is defined in that way, but what I can find in the covariance matrix is along the diagonal I can find the variance of each individual variable. And here I can find the covariance between x1 and x2. Here I can see the same. Okay, because the matrix is symmetric. Okay, so along the diagonal I can see the variance, and in off the diagonal I can see the covariance. Okay, so the covariance between these two random variables means how these two random variables are correlated. And what about if the correlation is zero? Well, the correlation is zero means that they are uncorrelated. Okay, simply that. So what we found, this is just a summary. What we found the following: that if I'm talking about two random variables. So if I calculate, the covariance of two random variables, xi and xj, which by the way, this is equal to the variance of xi when I equals j, and it's a cross correlation between I and j when they're different. Okay. Now, but we found that in this case, okay, so we found that when covariance this one, when this is equal 0, means that xi and xj are uncorrelated. Which means that if xi is Gaussian, xi and xj are statistically independent. And this is what we found. Further, if it is different from 0, then they are correlated. Right? And if they are correlated, then that means that I can say something on the variable I, provided that I know j. Okay? So this is what we saw. Now, what are a random process? A random process is a collection ordered by time. So it's a collection of random variables obtained by the time ordering is obtained by time. So, the stochastic random process then, if I consider, that means that I have a set of samples, x1, x2, xn. But where did I get these n samples? That means that these are the n samples obtained by a random process, which means is a set of samples corresponding to a time varying random process. Now these samples are ordered, which means the ordering comes from the time. So you can look at these axes as a time, and then this axis is the index n, and this is, if you like, is time. So time is ordering. Okay? Now this ordering comes from the physics, comes from the problem. Now the ordering were not existing in the previous one. Because if I go on the previous one, you know, and I take x1, x2, and x3, then you say, oh, but you know, x1 is ordered. Yeah, you know, I can put x2 on the upper part and x1 on the lower part, and all the properties, it doesn't change. So I can make similarly, and it is with the same property, I can make similarly, you know, a vector which is obtained by x2, x1, blah blah, and xn. So I'm swapping as 1 and 2. It doesn't change anything because it's just an ordered set. Now x1 can be, I don't know how much money I have in my pocket. x2 can be how many phone calls here. x3 can be, I don't know, how much rainfall came last month. x4 can be whatever. So in this way, here I am aggregating variables that are not necessarily homogeneous. So, see, I can have money, I can have, I don't know, I can have, what was the second one? A phone, blah, blah, blah. Okay, see, different variable. Here, the variable is the same. If xn is representing the stock's value, it's money. So x1 is the stock's value at the time 1. x2 is the stock's value at the time 2. Now, if that one is voltage, x1 is the voltage at the sample time 1. x2 is the voltage at the sample time 2, and so forth. Okay? So this one, you know, this time index can be representative of a sampled data. And so this might be 1 time delta t, if delta t is the sampling interval. And this one is 2 times delta t, if delta t is the time, if the sampling interval. So just to summarize about that, so if sampling a continuous time, xt, okay, if I sample that one, that means that I can extract by delta t capital. Okay, if I'm sampling this way, then you know this means that x n is equal to x n times delta t. So sampling is simply extracting the value of the signal at the regular interval delta t. So x n time sample, and you know the time word will be dropped. So the nth sample, okay, is obtained by sampling xt at t equal n times delta t. Okay, and this is the sampling. Now there is a way to sample the analog signals, or you know, to sample any signal, and it's not the goal of this course to discuss, because you know I assume it's well known. In case it is not, for those of you that you know you need to refresh, you need a refresh about the sampling theorem. Come in the break, and then we'll make it. Okay. So anyway, so we have this set of samples. Now these set of samples are random, is representative of the random process, and this one, if I take just a snapshot, is a realization of the random process, which means just that. Okay, so it's that value. So I can, since that one is this one is a random process, then I can define the same property I define here. So I can define the property of mean, because you know x1, x2, x3, sample 1, sample 2, sample 3 is, you know, it's a random variable. And then I can define the mean on sample 1. So I can, you know, I can write what is the mean on sample n. Now I try to use the square bracket on samples. Now after a while I will forget about, you know, it's, to make it quick I will make around the bracket, but you know, the principle should be square bracket. So when I can define, you know, the mean value for the n sample of the random process xn. Now this one is a certain mean, similarly as we did, except that, you know, this one might be dependent on the time index n. Okay? Now, if this one depends on the index n, we say that the process is not stationary. If this one, you know, we have that mu x n is equal to mu x k, or k different from n, then we say that it's a stationary on the mean. Okay? So what does it mean? It means the following. Imagine, you know, I have my random process and I'm sitting on a sample. The mean of the random variable, which is a representative of the random process at the time n, is the same when I make another step forward and I calculate the mean there. I make a step forward and I calculate the mean. If the mean is independent of the time sample, that is a stationary in the mean. Okay? Now, next, we can define on these random variables the correlation properties. So what are the correlation properties? I mean, so what did we do? We say it's on the other page. So we wrote covariance on xi and xj. Okay? That is for a random variable. But you know, now xi, which is the index I, is the sample I. And the index j is the sample j. So these are just, you mean the covariance between the two random variables I and j. And now I write the covariance between x I, x j. Okay? So I indicate this in a different way from the other, because the major difference is that here the index is ordered, okay, just for convenience. Here the ordering is because the time is ordered, is progressively ordered. Okay? Now this one is the covariance between I and j. What does it mean? It means that, you know, if the covariance is different from 0, that means that if I'm sitting on the sample I and I want to say something on the sample j, assuming that the sample j is in front of me, then if it is correlated, because the covariance is different from 0, then I can in some way predict the value of the sample j from the sample I. If I and j are uncorrelated, that means that if I'm sitting on sample I, okay, so that's, you know, that's me. This is the sample I, and this is the sample j. And in the middle there are others. Okay, so imagine that, you know, I'm sitting here and I'm looking there at the sample j. And you know, if I'm sitting on sample I and I want to say something, what is it that sample j correlated with me? Now, if it is correlated, ideally, if it is fully correlated, assume that, you know, it is fully correlated. What does it mean? That, you know, if this number is equal to 1, that means that if I'm moving up, the other is moving exactly like me. Okay? That means that they are fully correlated. If two random variables are fully correlated, okay, that means that this one is moving up and down. Whatever, the other is moving exactly the same way. Okay? This is the correlated. Now, they are anti-correlated. How is it -1? If this one is going up, the other is going down. Okay? This means the anti-correlation. Okay? That one is anti. Okay? Anti-correlated is when it's -1. And what does it mean 0? 0 means that if I'm sitting here, that one is fully uncorrelated with respect to myself. Which means, you know, if my value is going up, the other is doing whatever. They have nothing to do. There is no correlation there. Now, so that means that we might have different options. Okay, if it is 1, they are fully correlated, and if it is equal to 0, they are not correlated.
Does this require some normalization or the definition of covariance?
Yeah, there is a normalization. I will write it, but you know, I'm making reflection about the intuition, your intuition. Okay. So now if I'm in this case, it's not correlated at all. So I cannot say anything on J when I'm sitting on I. Okay. That is the case where they are not correlated at all. In some cases, we are dealing with this kind of phenomenon where the samples are not correlated. We will call it, white random process. Now, of course, I'm correlated with myself. So, if I make I equal J, then, I'm fully correlated in this case. Okay? Now, let's be, as you have been pointing out, let's be a little bit more formal on that. This is the intuitive aspect, okay? Now, so as we discussed, okay, we calculated, given the discrete time random process. So remember, this xn is a random process, so it's a set of random variables that are ordered in time. Now, we can calculate that given the random process, we can calculate the moments. And so the moments are, the mean. Now, this mean is a sequence. And when I indicate as a sequence, means a set of numbers. Okay? So the mean is generically dependent on time, on index n. And so this one is the mean sequence. Okay? So it's the mean sequence of the random process. We can calculate the covariance sequence, okay, or the auto-covariance. Okay? So the covariance sequence, which is exactly the one that we indicated there. And the covariance sequence depends on the two indexes, m and n. Okay? So that one, is reflecting the same definition we used before, except that, we are counting individual random variable reflecting to the time position as the two variables that I'm aggregating, I'm using for the covariance measurement. Then I can calculate the autocorrelation sequence. So the autocorrelation sequence, or simply autocorrelation sometimes, we will say autocorrelation, okay? We will say autocorrelation sequence. Sequence, remember, sequence means that this one depends on the index. Okay, this is the sequence. So we have the autocorrelation sequence, which is reflecting the degree of correlation between xm and xn. Now, according to the definition, if I consider the autocorrelation sequence, then the autocorrelation sequence is correlated, so it's correlated, is mathematically linked, okay? Because otherwise, you know, we confuse correlation. So it's mathematically linked with the covariance sequence and with the mean sequence, okay? By this formula. So that means that, you know, the correlation is equal to the covariance sequence plus the mean. But you know, if the mean is 0, and by the way, this is a very common assumption. So if the mean is 0, the correlation sequence and the covariance sequence coincide. This is very important. Okay, so you know, for mu x and identically 0, then the autocorrelation coincide with the covariance sequence. This is a common assumption. And this justifies the fact that I will use most of the time correlation sequence, because I'm assuming that the random process is 0 mean. Now, once again, you know, we can calculate the variance, and the variance is the correlation with itself. Since I took these slides from the book contains in parallel the continuous time random process and the discrete time random process. I'm realizing now that some of the notation still remains. So I need to put it n, and that one is cxx and x. Now, further, the variance or the covariance sequence calculated, you know, within a certain point is always smaller than the product of the two variances. And I can define the correlation coefficient. What is the correlation coefficient? The correlation, let me see, here, no, I'll tell you. So the correlation coefficient will go here. Okay, correlation coefficient is cx square and divided by the cx and cx and n. Correlation coefficient depends on n and n. And so what I was discussing here about this number, 1 minus 1, so on, is related to the correlation coefficient. And so the correlation coefficient, as you know, I said, is equal to, let me move it here. So the correlation coefficient, you know, is lower than 1. And it is equal 1 fully correlated. It is equal to minus 1 fully anticorrelated. And it is equal to 0, okay, when, of course, everything is for n different from n. And is equal to 0, that means that fully uncorrelated. Now, let's move a step forward. So up to now, you know, m and n are two indexes. Now let's assume that my random set, so this random set is composed by n random variables, and then I can calculate the joint probability of this random set. So I have this set of variables. Okay. So I make a vector x, and this one is x. I mean, look at here. It's x, k, x, k plus 1, x, k plus 2, x, k plus n. Okay? So this is a set of n random variables. Then I can write the probability density function for this set. I'm not saying that they are Gaussian, not yet. Okay? So I can write that notation is notation for continuous sign, continuous time. Okay, so now I can stack all these n values. I can calculate the probability density function of x. But this x, is related to k and k plus n. So this set starts with k, which means I'm taking this random variable starting with k, and then it is k plus 1 until, I have k plus n. Okay? So I'm using, this random set. Now, if I use this random set, I can calculate, let's write this way. Okay? Then I can calculate this vector that depends on k. So I can write the joint probability density function on this random vector. This joint probability density function depends on k in general. Okay? Because I'm taking these k and samples starting from k. Now, but if the probability density function, okay, that depends here on k, is independent of k and is equal for any value of k, any choice of k. So if the joint PDF for the n random variables is equal to the joint PDF for any, this is k, this is n. It is equal to the joint probability density function for an index m different from k. So if the probability density function for a signal that I cut it here is equal to the joint probability density function for a signal that I cut it there, then, if this is valid, we say that the random process is stationary. It's stationary in the so-called wide sense. Okay? So this is the wide sense of stationarity, which means it's stationary regardless of the position where I pick up the k value. So which means, here what I'm doing, I'm measuring, measuring the voice. Okay, you have a microphone and you measure the voice. And you segment, which means segment is slicing the random sample. So you segment the random process at a specific k sample. Okay, so I'm slicing one. And I slice another one, moving forward. So the two random, the probability density function of the random set 1 and the random set 2 are not necessarily the same. If they are the same, independent of the origin of the axis, we are saying that the random process is stationary in the most general sense. Most generally say with the wide sense. So we say it's strictly stationary, which means nothing depends on where I'm copying the data. If they are not, they're different, trouble. If they're different, that means if I'm cutting the data here, I'm cutting the data there, makes totally different. Okay? Now, let me make one stupid example on that. Example of non-stationary. Okay, I have, a set of measuring point in space, in different geographical areas. Okay, these are measuring earthquakes. These are measuring earthquakes. So this is, I don't know, this is, if you like, this is Italy. Okay, this way, down, and so on. Okay, this is Italy. Huh? So we measure all that, and we take the signals from each of them. So, if I measure all that, I'm measuring some noise. So number one is measuring noise. Okay, this is number one, number two, number N. Okay. So each one is measuring the noise. Okay. Oh, good. Then the degree of noise might be local dependent, but it's more or less the same. Okay. Now, unfortunately, this is done for many years. Okay, doing nothing. But at a certain point, one is measuring that. The other is measuring that. The other is measuring this. Okay. So now let's reason that. These signals is a random process. And it is fully stationary there. It's stationary because, if I slice any interval here, the behavior is similar to there. It's similar to another interval. And so forth. Okay? Nothing changed. But at a certain point, this interval, if I consider this vector and that vector, and I calculate the probability density function for the vector in the noisy area and for the vector in the active area, the probability density function, they are not the same. I'm not saying Gaussian. You see? I'm not saying Gaussian. Okay? So the behavior is totally different. So it is different than, this random process is surely non-stationary in a wide sense. Because it depends on where I'm considering the random process. Okay? So most of the theory is done for a stationary random process. If a random process is non-stationary, which is unfortunately for you is mostly the case, then it's trouble. Then comes your job. If you have to do with a stationary random process, you have a lot of theory. Having a lot of theory doesn't mean having a lot of headache to study. It means having a lot of theory which supports your computation. Imagine that you want to predict the earthquake, okay? And and you have a lot of theory which is describing the behavior of the noise before the earthquake. So you can say, I know perfectly. So in case someone say, oh, but you did not predict the earthquake, then you say, okay, but I used the theory. The beauty of the theory is that it releases your responsibility. Clear? Okay, so you understand with the earthquake, the responsibility concept. Huh? So, but in this case, since this one is non-stationary, if you say, I use the theory for stationary random process, and then you go in jail because you made a mistake, because you used the theory for stationary process, and this earthquake is non-stationary. Okay? So, now, let's go to the point. So, stationary now means that is the same statistically. Okay? Which means the probability density function within the segment are the same, if stationary. Now, since the wide sense of stationarity is so difficult to verify, since you know it is so beauty, but is we are not always so sure that is fulfilled. Since the random process is mostly Gaussian, that's another story, but it's not always Gaussian, then we use another definition of stationarity, which is a stationarity on moments. Okay? On moments. And what kind of moments did we see? You know, we saw the moments, the first moment and second moment. First moment is the mean, second moment is the covariance. And so we can establish the stationarity on the mean and the stationarity on the covariance. And this is what is called the strictest sense stationarity definition. Okay? So we will see that now this degree of stationarity. Now, in the stationarity in a stricter sense, means that this is for discrete time. This means that the mean does not depend on the index n. The mean is the same over the time index. And the covariance is not dependent on the absolute time. It depends just on the difference of time between two samples. And so now this means that the covariance is equal to x multiply xk n plus k, okay? And when I take the expectation, this one depends on n. It does not depend on n plus k, because k is just a displacement, it's a difference between, n is a difference between k, okay? So I'm sitting on the sample k, and I'm correlating the sample k with the sample k plus n. So, and you know, if I move another step, and I correlate myself, the sample k with another one in front, and or the other behind, and you know the correlation is the same. Now, if this is valid, then we say that the process is stationary in a strict sense. Once again, keep in mind, I forgot to write it, keep in mind that, you know, if mu x is equal to 0, then Rx x n coincide with the covariance sequence depending on that. Okay? And there is a Schwarz inequality. Now, you know, there is some properties. For instance, the covariance is even. Is even, you know, so that means that if I calculate the covariance on plus n and the covariance on minus n is the same. So stationary means that there is no orientation in time axis. Because if I calculate the covariance between myself, k, and k plus n is the same as covariance between myself and k minus n. So that means that the time orientation does not exist. Which means if I'm sitting on one sample, the correlation in front, 10 samples in front, 10 samples behind is the same. This is the meaning of this, you know, the even behavior of the covariance. And that one says, if I'm calculating the covariance between me and that sample, that covariance is smaller than the covariance between me and myself. Because in this case, that covariance is called the variance. So the variance is always larger than any other. So if I now sketch the behavior of how, by using these two rules, how the covariance should look like, it should look like this way. So I take the sample, this is the sample n. Now what I'm writing is the covariance. Huh? I have a sample n, in 0 I have a certain value, but then you know the behavior is symmetric. And in 0 should be larger than all the other. Okay? So for this property, in 0, it should be the largest one. So this is, you know, Cx x0, and this is minus Cx x0, okay? So everything should be lower than that, should stay here. And so the autocorrelation, by the way, or the covariance is symmetric. Is even, okay? So I have sample samples. They are decreasing or whatever. Okay? Or perhaps they might be this way. Okay, but you know, cannot be larger than 0. Now, can I say property here? Suppose that this is the same of the previous one after 22 samples. What can I say? Reading this autocorrelation or autocovariance. Now, if I read this autocovariance, that says that if I'm sitting on a sample, then the more I move apart, the more the samples are decorrelated with myself. But at a certain point, after 22 samples apart, that sample is moving exactly like me. 22 samples apart. So 22 samples apart, you know, they're moving exactly the same way. So the sample in the middle, they're moving, and you know, if I take in the center, their correlation is close to be 0. Okay? So one is moving, the other is moving totally different way. Then when it's getting closer, you see, this is the behavior. Now what I'm mimicking, okay, like a cartoon here, if you go to MATLAB, it takes 0 to prove it. So I encourage you to check it by yourself. Now, let's see some typical random process. Now, let's consider, for instance, a wide process. So what is a wide process? Now, the wide process, the samples where the samples are 0 mean, you know, and then the process is self-correlated only. So it's correlated only with itself. No, if I look, don't look at that. Okay, so see the book for this. So if you are interested in continuous time. So if I consider the wide process means that xn and xn, they are not correlated when n is different from n. N is correlated only when n is equal to n. So I can simply write in a compact way that the autocorrelation is equal to 0 anytime when n is equal to n, is different from n. And I indicate by the delta function. The delta function, remember, delta function is delta k means that it's 1 when k equals 0 and 0 when k is different from 0. Okay, so when I write it this way, that means that this delta is equal to 1 when m is equal to n. Okay, so in other words, this means that this is equal to sigma square when m equal to n, and is equal to 0 when m is different from n. Okay. Now sigma square, in this case, indicates the power of the random process. So the variance is the power in our case. It's the power of the random process. Now let's take another case of another different process. This process is called exponentially correlated process. Okay? So this exponentially correlated means that the covariance is behaving as a sigma square multiplied by rho with the power of n minus n. And the absolute value of rho should be smaller than 1. Now, rho can be complex. Okay? Rho can be any. So the only constraint is that rho is smaller than 1. This is the constraint that we have. Now, what's this? Okay, so this one deserves some discussion. What does it mean? Now let's have the one page, okay, to discuss a little bit more of that. So let me copy this and paste. Okay, now what does it mean this way? So you need to consider, let's consider the case where rho is real. Okay? When rho is real and and the process is stationary, strictly sense of stationary SSS. Okay? So strictly sense of stationary means that it is stationary only on the mean and covariance. Okay? First and second moments. Now, if this one is the case, then this CXX depends only on the time difference, and the time difference is k. So that is sigma squared times rho to the power of k. Okay. If this is stationary. Now let's look at that. So what does it mean? It means that if I choose, for instance, if rho is equal to 0, then that means that this exponential process is, if rho is equal to 0, means that if rho is equal to 0, then 0 to the power of 0, then I need to consider the limit. So 0 to the power of 0 makes 1. So if this is the case, then my CXXK is equal to sigma squared for k equals 0 and 0 for any k different from 0. So we have now the so-called white process, because the white process was a process where every sample is correlated only with itself and not with the others. This is a white random process. So we degenerate into the white random process. Further, okay, this, since a rho is smaller than 1, then my autocorrelation is exponentially decreasing. And for k going to infinity is 0 anyway. Okay? So that means that I'm always decorrelated with a set of samples that is very, very far away. So for k going to infinity, then the CXXK is going to 0. But always I'm correlated with a sample that is in infinity. But I can also notice something. I notice that, since a rho is defining the subtangent, then I can find the interval where, I decorrelate myself. So that interval where I decorrelate myself, okay, is the interval where my correlation is decreasing by a certain level. Okay, so I can define an interval of decorrelation. So if I can say that, my decorrelation interval, so this decorrelation interval that I indicate as n row. Okay? So this n row is the decorrelation interval, is the interval when I decorrelate by, for instance, 90%. So let's say, what does it mean? It means that, if I consider, I make the ratio between the full correlation and the correlation at n row, and full correlation to sigma square, okay, which is, that one is the correlation of covariance in n row, and this is the covariance in 0. And this ratio can be 1/10. 1/10 is the correlation by 90%, because the only left is 10%. So I can put this equation into my formula, and then I get I can calculate that the logarithmic for that. So it's calculating log 10. So I have a number of samples, okay, multiplied by log 10 on the row is equal to minus 1. And then I can calculate n row. So n row now means the number of samples that are necessary to decorrelate by 90%. Now, this correlation is indicating how much is predictable, how much one sample is similar to the other. If the decorrelation is 90%, which means that the only left on that sample, which is correlated with me, is only 10%. So I cannot predict very nicely what's happening at the distance n row, because it's loosely correlated with myself. So it's very easy to predict something that is fully correlated with you, and it's very difficult to predict something that is loosely correlated with you. Considering the correlation like the periodic one. Do you remember the periodic where I said, where did you put it? Here, that one. Okay, I'm a sample 0. And then, after 22 samples, a correlation is 1. Excellent. Then let's put it another way. Since after 22 samples, that one is fully correlated, if I need to predict the value of the stocks, I use the one of 22 days before. And then it's exactly that. Is it clear this way? You like this way more? Okay? More by visual, huh? Okay, so that is the importance. If I try to predict correlation 0, okay, so 11 days, correlation is 0. What does it mean? It means that if I try to predict the value of the stocks, okay, by using the data, so if I'm sitting here, I try to predict the value of the stocks 11 days ahead, forget about it, because I would do a big mistake, because it's uncorrelated, correlation 0. There is no, it doesn't say anything. 11 days ahead, it doesn't say anything on the value that I had. Okay? So, but since the behavior is this one, so I take 11 days on the back, and then it's predicting exactly the value of 11 days ahead. So I can make a lot of tricks on that based on the behavior of the correlation function. So it's talking. If you read it, there is a lot of content. And similarly here. So if it is decreasing, okay, that means that I can predict a lot on the first samples, 1 sample, 2 samples ahead. But after a long time, infinite, we say far enough, long enough. Okay? So after a long enough interval, I cannot predict anything. It's unpredictable. So I better to throw the data away. Okay? So let's go to the prediction of the stocks. Because I told you, my goal is to make you rich, one way or another. So if I don't succeed with with engineering, let's try to do whatever, okay? So, you know, that, if I look at this formula, let me look that. So, now I'm telling you that rho, okay, in stocks data, rho is equal to 0.9. Okay? Someone, God is telling me, okay, assuming that exists, God is telling me that rho is equal to 0.9. So if rho is equal to 0.9, then it's very important for me. Because, you know, what I can say, what can I say? I can say the following, that, you know, this is the behavior of the stocks, okay? You know, I'm sitting now here. Okay, this is now. My goal is to predict the future. So this is tomorrow. So it is, this is now. Now means n. So what I want to predict is n plus 1, right? This is my goal, okay? So since what I want to predict is tomorrow, now, you know, tomorrow is correlated with itself, of course, you know. The value of the stocks tomorrow, you know, is fully correlated with itself. Now, how much is correlated the data of tomorrow with me? So what can I say on the data of tomorrow with respect to me? Well, I can say that, you know, the distance is 1. So if the distance is 1, then the correlation is here is sigma squared multiplied by rho to the power of 1, which is sigma squared times rho. So since a rho is equal to 0.1, that is a 0.9, that is 0.9 times, okay, that rho. So the correlation of today with the future is rho times sigma squared. So rho is 0.9, so it is 0.9 sigma squared. So that means that there is a 0.1 which is left unpredictable. So I can predict anything but except 0.1. 0.1 is left unpredictable. I cannot say anything on that. Now, let's make the two samples behind. So let's make now and yesterday. Now, since the correlation property is decreasing, actually decreasing on the other way, but you know, I don't have the future, okay? So that one is decreasing, then this one is fully correlated with itself. That is decreasing on 0.9. This is 0.9, so it is 0.81, which is 0.9 to the square. 0.9 to the cube. Here is 0.9 to the 4th power, and so forth. At a certain point, you know, this is 0.9 to the power of something, that will be negligible. If it is negligible, that means that looking from here, so imagine that now this one is close, how much is that? I think it was 5 samples with 0.9, but let me make it. Oh, I can give you the number. 0.9 power 3, 0.72. 0.6. You know, at a certain point, you know, let's say 10 samples. Okay. At the 10 samples, otherwise, you know, I need to replace that number by number. After 10 samples, this rho to the power of 10 is approximately to 0.1. Now, what does it mean? It means that these are samples 10 days behind is correlated 0.1 with that. It's very small correlated. It's not having any much information on the information which is related to the future. This one now is a lot of information. Yes, 2 days behind, 3, 4, 5. but 10 days behind. It's not adding as much information. So what does it mean? It means that, I'm using only this data to predict the future, not much behind. I am taking only the first part of the data to predict the future. Because, virtually, one can use all the data starting from the past, starting from the 10 years before. And 10 years are not correlated with what's happened now. So what's happened now is correlated, okay, with what's happened very soon. So the day before, 2 days before, and so on. It's not far away. So this is another way to interpret that. Now, these exponentially correlated signals are very important in our semester and our job, okay? And these are typically called also the autocorrelation random process. Autocorrelation random process, autocorrelated, is called AR. Okay. Now, let's make another one. Sinusoid with a random phase. Let's assume that I have a sinusoid with a random phase. This is the process. Now, let's look at with detail. Okay. Now, a sinusoid with a random phase is a process because the phase is random. So, let's consider the case where, at the sinusoid, A is deterministic, omega is deterministic, but phase is random. Now, is it a random process? Well, since every experiment I can choose a phase and the phase is random, this is a random process. It's random because the phi is random. It's random because the phase is random. Now, let's assume that, the phase is random and is taken by uniform distribution between minus pi and pi. This minus 180 degree to 180 degree. Okay. So now I can try to evaluate what is the statistical properties of this random process. Now, first of all, let's take these signal shifted. So let's shift by n samples, arbitrary k samples, these are sequence. Now, if I shift by k samples, what's happened is that I have a cosine, then I have omega 0 n plus phase minus omega 0 k. Okay, now k is arbitrary. Now, what's happening is the following: that if I look at the phase here, the new phase is this one. So this phi naught is this phase phi minus something. But the phase is defined between minus pi and pi. So since the phase is defined between minus pi and pi, then the resulting phase when I remove something is still random, because it's a random variable plus a constant or minus a constant. But since the phase is random and is random and uniform, it doesn't matter if I had something. So what I'm saying is that, the random phase means that I have a random vector here. And this is phi. But this phi, because it's random, is, every time I make a realization, then this phase is random itself. And it's going here, there, okay? Every realization. So now, what's happening if I add the constant on that? So if I add a constant, it is still random. And if phi is uniform, if I add the constant, it is still uniform because the phase is constrained to be between minus pi and pi. So if I have this one, this phi, and I add the constant, this is the constant term, alpha, if you like, okay? But now, since the phi is random, everything is rotating. And it keeps rotating in a uniform way, so the resulting one is uniform as well. So this is the essence. Now, when I write that phase as a modulo, do you know what is modulo? Modulo 2 pi, modulo? Modulo means that, the phase is measured modulo 2 pi, which means, what I measure as a phase is independent of how many rotation, because I cannot see how many rotation the phase did. For instance, if I give you this phase phi, and if I make this phase rotate by 2 pi, so if I say 2 pi plus phi is the same, you cannot notice how many rotation I did. So since you cannot notice how many rotation I did, this phi and this 2 pi plus phi is coincident with the phi. Now this writing, it makes no sense. And in order to make sense, I need to say that the phase is measured modulo 2 pi. Which means it's measured between minus pi and pi. And everything that you measure on phase is wrapped within the interval minus pi and pi. If I make a nice plot here in the board about, the phase evolution, then I can make these nice evolution about the phase. But this evolution about the phase is not measurable. You cannot measure it, because the phase is measured between minus pi and pi. So what does it mean? It means that if this is the minus pi and pi interval, so this goes here, this goes there, this is going this way. This is the phase. This is the behavior of the phase wrapped, which means evaluated modulo 2 pi. Okay? So this is what you measure. That one is what you would like to measure, for instance. Okay? But since the phase is modulo 2 pi, it goes here. So because of that, now I can evaluate the property of this random process. Now the random process, remember, is random because random process is random because the phase is random. I always need to keep in mind what is random. When I measure a random process, I need to see what is random. Now, let's see, what is the mean? So, if I need to evaluate the random process, I need to see the mean. So what is the mean of x? So the mean of x, is the expectation of this number. But this expectation is calculated with respect to phi, because phi is the only random variable. Now, if I take the expectation for that with respect to phi, I can write as by the trigonometric rule. So I have cosine, cosine, sine, sine. Okay? So if I write the cosine, cosine, and sine, sine, then the mean of cosine, the mean of sine is 0. And so because of that, the mean value of this random process, which is a sinusoid, is 0. Now, next, let's calculate the autocorrelation. It's 0 mean, remember, it's 0 mean, so correlation covariance is the same. Okay? So let's calculate, the correlation properties. I use the definition. So by using the definition, I have xn and xn plus k. This is the definition. Now what I do, I simply take, in place of xn, I make a copy of this a cosine. In place of xn plus k, I make a copy of this one with n plus k. Okay? So, this is what I did. And then I multiply. When I multiply, I apply the trigonometric rules. Okay? Then I have a squared divided by 2. Expectation, remember, you see, with respect to the random variable, phi. Okay? So, is the expectation of the product. So I have an expectation with respect to phi of cosine omega 0 k. and then I have the expectation with respect to phi of cosine 2 times omega 0 n plus omega 0 k plus 2 phi. So I have the expectation with respect to phi of this number. So what is that? That one, you know, is a uniform distribution. Now, if the random variable is double, it is still uniform. If I take this random variable and I sum on or remove something, a constant term, it's still uniform. So this is 0. Okay? So that one is 0. Okay, for this reason. So the result is that the autocorrelation is a squared divided by 2 cosine omega 0 k. Nice. So that means that in this case, the autocorrelation goes the following way. So it is exactly versus k. It is 0, so it's going this way. Remember, this is not the sinusoid, this is the autocorrelation. So when I'm sitting here in 0, the sinusoid is fully correlated with myself. But you know, after one period, it's fully correlated. After 2 periods, it's fully correlated. So in this way, I have a way to measure the period. Because if I take a sinusoid with a random phase, and then you know the sinusoid with the random phase is fully correlated after, so every period. Second, I can calculate, you know, given the autocorrelation, I can calculate the power. So the power of a sinusoid is when I consider Rxx or k equals 0. So that is a squared divided by 2, which is what you know is the power of a sinusoid, is the amplitude squared divided by 2. So what we have now is the autocorrelation property of a sinusoid and you know the power of a sinusoid. By the way, the sinusoid in random phase with random phase, I think it was one of the written exam was one of the basic questions, I think, if you go in the past. Okay. So some remarks before we make a break. So remarks. Remark number 1, okay, is it's a Gaussian approximation or Gaussian assumption or Gaussian is mostly used. It's very common. Okay. The reason for Gaussian is very common is because you only need to know the mean and covariance. So it's enough to have the knowledge about the first 2 moments, first and second. Okay. And the other remark is often processes are 0 mean. Okay. And all the derivations are for autocorrelation. So I mean, what I'm doing is most of the cases, I'm considering the process, the random process as 0 mean. Nowadays, all mean is removed with the signal manipulation to reduce the 0 mean assumption. Okay. Now let me explain this word. If I know that a random process is not 0 mean, okay, so assume that I give you a random process. Okay, I give you the sinusoid with a certain constant. So this constant, you know, assume that I take a sinusoid and I shift up. So if I shift up a sinusoid, that means that the sinusoid is a non-zero mean. Okay, because you know, the mean value is based by how much is shifted. So usually the mean of the signal is non-informative. It's not important. It's not relevant. Now let me make there are electronics, right? Here, okay. Let me make an example for the electronics, our electronics Otherwise, you know, I'll make an example for everybody except that. You commonly use or remove the zero mean. I mean, when you do the electronic circuits, okay, and what you do, you use the zero value, the zero mean value, to do a specific procedure, which is called the bias of the circuits. So what you do, you make a polarization of all the circuits. So you shift the signal with respect to the zero in order to have a DC component which is controlling all the voltage that is necessary to give the power to each of the specific device. So this is common. So you remove the mean in a specific way in order to use that mean value to just, you say polarization, right? Is it called this way? Okay. So you make a polarization of the circuit. Polarization is when you take the circuits for the others, and you know the circuits has to work within a certain frequency range. But the zero frequency is not used because the zero frequency is left to control the voltage of the circuits, to let it work. And electronics, our electronic colleague, they have a nice devices which is blocking the zero mean, which is called capacitors. So in electronics, they use, our electronic colleague use you know, the capacitors to block the zero mean. So when I say, you know, I have a sinusoid with a zero mean, I simply put the capacitor, and then the mean is constant. Okay. So for this reason and many others, like for instance the second one. So let's make another example. Okay. I mean, by the way, just for the electronics. Okay. 89, from 1989 till 1995 or 1996, I've been teaching electronics for telecommunication. Okay? So it's only because I don't remember. Huh? So, you know, I'm supposed to remember now. I'm refreshing. When I talk, I refresh. Okay. So for instance, transformers. So when you have a transformers, okay. So when you have an inductor and stuff, you make a transformers. When you make a transformers, you know, I mean, all the DC component is blocked because you cannot transform a DC component. Okay. So when you have a transformer with all the coils, right? And then you know, you make transformers in this way. All the DC component is blocked, so it's not used. And then that's another way. So you know, you can use a DC component. Okay, so there is many technical ways to remove the DC component, and the DC component is not useful in our reasoning. So for this reason, okay, I mean, everything that I'm going to discuss is not made with a mean that is different from zero. So I would make everything with a zero mean, and I would remove the mean of the random process whenever it is necessary. Then we do after the break.